shit. Oh, sorry. Sorry about that. Yeah, there should be sound now, right? Yeah, yeah. Sorry, I haven't said anything except I'm gonna get ready to start. Let me just like write the agenda. Yeah. What is even what has happened? It's I code not too long ago. You started learning to code. Okay, okay, that's cool. That's cool. This might be uh yeah, since this is formally verifying stuff, it was a bit above introduction, but that's okay. Didn't see a lot of people in here. Oh, that's cool. Yeah, yeah. This is like, yeah, not many people do it. So, um, probably get done with denoting. Okay. Great. Just do the thing. What did I last time? Agenda. HTML, JavaScript, CSS. Great. That's good. That's good. That's a good place to start, really. Okay. Let's just take a look at that. Am I stupid? Yeah. Okay. Perfect. See here, this should have the agenda. So, I guess we should just give it a go. Just give it a go. Make that. Yeah. Yeah. All right. Okay. Okay. Let's get ready. Yeah. All right. I guess I'll give that. I guess I'll start. All right. So good morning, everyone. Good morning. What's really uh been done since before and now? I guess I'll show. I'll just show. Um. So let's just take a look. So here it was last stream. Um. Oh, where was the stream? Yeah. Okay. Apply rewrite correct. What stream? What stream was this? What stream was that? Was this one? Yeah, this one. This one was this one. Okay. So since then, there's been this commit, this commit, this commit, this commit, this commit, this commit. Really, those two commits, like not two, those couple commits, is really just to get over that bump that I had last time, where it's like, okay, how do I why is this not definitionally equal? I guess I'll show that off. So if you go to reify, here, right? I was like, okay, why isn't this definitionally equal? Actually, I think I can show. I can show the like just issues that I had. It was just like, what are the issues? What are the problems? Yeah. Okay. Maybe I can find. Maybe I can find like an example. Was it MWE? Hold on. Let me go to an earlier version of this. Where's the MWE? Oh, sorry. Give me a moment. Yeah. How do I just like switch to this? Or just like show me this? Framework of proof generation. I'm trying. What's this one? Okay, this is the one. So, I guess my biggest problem was, really just getting this to work. So, here you go. Here's this. So, okay. So IR eval, the definition of IR eval, it takes in a width assignment and then takes in an actual assignment variables. The reason why, how it works is it's basically like an interpreter. So it takes what's it called? It takes the IR, and remember the IR is basically just the AST, variables, constants, poisons, adds. You can take on two sides, takes two different IRs. So this is more like an AST. This is an AST. So each IR is parameterized by like a IDX. It's like index. You just write it like this, right? IR IDX, like IR 0. This 0 means an index into the width assignments. So how to actually type this IR is you don't type it like this. Previously, like I had like an IR, like IRN, right? I would type it like this, IRN32. Okay, this is an AST. It's just typed as like this returns a 32. This returns like a 32-bit this thing, right? So how the signature would work is that ir.eval really just takes in this and returns this, like up to assignments, right? Up to assignments. But how it works now, or how it worked last stream, and how this is like the real deal. This is how things are gonna work. Is that it's not parameterized by bit width. This thing, this nat here, this is parameterized by index. Parameterized by index, and this is an index into the width assignment. So what is the width assignment? So this is xi. I think that's how you pronounce it, right? Xi, xi. This is xi. It's basically an array of nats, right? So if you have an IR IDX, so if you eval this, so ir.eval IR IDX, like of some IR IDX, this would return a in xi get IDX. That's how it works. So previously it would have been previously it would have worked like bits. This would return an in bits, but no, this is this. The reason why I do it this way is to handle polymorphic like for all bit widths. So for example, if I have a program, right, function n, which takes in an x in and just returns something, right? This program is basically like for all n define a function n n returns x. This is like this function is defined for all bit widths. It's not just like an any old function. So basically, to perform rewrites on this, right? If I had an IR, so let's say I turned this, right? I took this, I did reify, so this would spit me out an IR, right? This is a meta program. It would take the lean expression and turn this into something useful. So this would give me an IR, but what IR, right? It can't give me IR32. It's basically going to give me a for all n define IRN. this program's defined for all bit widths. It can't return to me an AST that only works on a single bit width. So the way I get around this is this, right? Xi is something, right? And this is just an array, and this is just like oh wait, no, I define it like this. So for all assignments, so basically I basically return the pair Xi IR 0, right? This is a pair. And then when I eval this, right, this will return to me in this xi get 0. It's sort of like a pair. So this doesn't exist for like in the real world. It exists as it's constructed as part of the meta program. So for example, the elements in here, right? This is basically equivalent. This is basically equivalent to INN, right? Because this is created by the meta program by just taking this expression and just like stuffing it in here. That's how it works. So, yeah. It'll show itself eventually. But yeah, I think this is just an explanation of what happened last time. Right, I explained it last time as well. So this is like an interpreter. This is an interpreter, straight up. So it takes in the width assignments, right? These are the types, like this, right? And it also takes in this sigma. This is just assignments. So this is just like wherever the vars are, it reads from here, right? Wherever the vars are, it reads from here. Whenever you need a bit width, right, it reads from here, right? So if you want to prove something correct, you have to prove it for all width assignments, for all assignments given those width assignments, and then prove that LHS rewrites to opt LHS. That's it. So this is a proof, and this is opt.wellformed. And that's in the rule definition right here. That's it. It's in the rule definition. So the implementation is a function that takes an IR IDX to IR IDX. That's it. So yeah. So yeah. Okay. So when we reify, I think I just like left a comment at the bottom, right? I think if you saw last stream, you would remember this. I just went over this as like the logical model of how I'm going to do all of this, right? So this is called a proof by I don't know, proof by reflection, proof producing tactic, something. Basically, let's say you have an IR, right? These are two meta programs. This meta program is called reify. It takes in an expression, a lean expression, right? So it would be like, for example, this function here, right? It'll take in this function. Lean can turn this into a lean expression. Think like run elab something. How do you do this? How do you do run elab? I'll do. Okay, so we can turn this into an expression. So I think let t just q quote this, right? Log info m t. Okay, so we can turn this into an expression. What does it look like? That's not right. How do I turn this to expert? This is expert, right? Great. Okay, this is we take in these functions. Reify is a meta program, so it really works on an expression. So for example, this is really this function here, right? It's a lambda, takes in this app. Yeah, it's just this. It's two lambdas, because this is the like first bind, this is the second binder, and then it returns the bound var 0. So this is just an expression, Lean expression. So reify takes in these Lean expressions. It returns the IR and a proof that evaluating that IR is equal to the expression. Then we have denoting, which is the inverse operation. It takes in that IR and then returns an expression, and then returns a proof that that evaluation of that IR is equal to that expression. They're basically inverses of each other. So how the rewriting is going to work is first, you get an IR. You reify the left-hand side, you get an IR. Optimize that IR to get IR tack. And then, so after reifying, you get a proof, right? That this IR is what it says it is. And then after optimization, you get a proof that rewriting that IR to the new IR is okay. This is like a valid transformation. This is up to well formed. And then you use the inverse operation. So you use denoting. So you take the optimized IR, you denote it, you turn it into RHS, and with a proof that this IR is what it says it is. And then you can chain these proofs. So we have three proofs, right? We have the proof going from LHS to IR. We have a proof that goes from IR to IR tack. Oops, sorry. And then we have a proof that IR tack rewrites to RHS. If you chain these all, see you have this, right? This is equal to this. This is equal to this. But this rewrites to this. But this is just equal to that. So you chain these. So it's just LHS rewrites to RHS. That's it. That's it. And that's the whole thing. It's just super simple. So I just need to implement these two operations, and then I'm good. I'm good. So reify. Yeah. So I think I skipped over the issues with reifying. So basically, reify is a recursive function that matches on basically whatever expression it can find, right? Let's say if it finds a poison in here, let's see, let's like this, right? Check. So if it finds like an X in here, or if it finds a poison, right? If it finds a poison, so it's a recursive function. If it finds a poison, it'll basically return the IR poison, right? And then the proof that that thing is actually equal to that thing. So in this case, right, it'll return a proof that ir.eval, I guess some, this is like a dummy, these are like dummy assignments to xi and sigma. And then it'll take in a ir.poison, 0, right? And then this is equal to poison by RFL. IN, N, N, and then X. This is type this. IDX. Oh, this thing. IR 0. It's equal to poison. INN. X is INN. This is type this. IN bits. Oh, I just fucking spelled it wrong. Okay, so this is so for example, so here, right? This is the proof, right? So when we return this, right, reified IR is basically a structure. It's something we want to construct when we return this. So it's the IR expression. It's the IR, right? This is the like expression of that IR. It just doesn't matter. This is like not that important. This is just the IR, right? The original expression and the proof that evaling this on the current assignments, right? Evaling this IR is actually just equal to this, right? So it's just the thing that we reified and a proof. So it's a pair, the pair of a thing and the thing that we like the proof that it's actually that thing. So poison is pretty simple. so it's basically just saying, so for example, for any assignment of these, right? This is your sigma, this is your xi. If you put a poison in, you get poison out. This is definitionally true, so it requires no proof. It requires no proof. So I just use RFL here, RFL in the same way I use RFL here. It's definitionally equal, requires no proof. But for here, right? How do I prove that if I use var 0 and the 0th var, right? This is the 0th var is x, right? The 0th var is x. If I evaluate the 0th var and I get x, like this isn't true by definition. Unfortunately, it's not. Unfortunately, it's not true by definition. The people, the tactic that I'm inspired by is BV decide. Since they don't rewrite bit vectors for all n, right? They only work on goals of the form, like, I don't know, bitvec 32, bitvec 32, bitvec 8, right? Since they work on these goals, this is definitionally true, but because I work on goals of like INN, this is for all bit widths. This is a quantified thing. Definitional equality just fails here. And I think I have on the zulip, right? I think on the zulip I wrote something. But yeah, if you look at the eval here, it's just a bit complicated. Like this is the exact same thing as BV decide, as what BV decide does. But it's just like more complicated. Because for example here, right, pack n, this is a symbol. It's not an integer. This thing is also a symbol as well. It's not an integer. Well, it is an integer. They're both integers, but it's like symbolic. So definitional equality just like fails there. Maybe I can find definition. Here it is. Here it is. Yeah, here's my like question that I put out on the zulip. So I was like, okay, why is this not definitionally true? Because it works for BV decide, and why me? So I was thinking like, okay, it's probably because I have n here, right? It's not like numeric values of n. It's for all n. Here's this, right? So if pack n is equal to this, the way decidable. So this is here, right? If you have a proposition in an if statement, it uses the decidable. It uses the decidable instance, right? So this is like a decision procedure, which checks if two things are equal. Here, right? It's a decision procedure for equality of natural numbers. So it's just like checking if they're equal. So this decidable equality. This works for if you have like a 32 on this side and a 32 on that side. But if you have like an n and an n on this side, this doesn't reduce. So that's why it doesn't work. So I have to prove this properly. So unfortunately, yeah. So the solution to that, and the solution that I used is so here, right? So this isn't true. But if we go to reflect, I use this instead. So I use this theorem. This theorem is basically saying if you have a width assignment and a assignment, given these two hypotheses, so if you actually getting the variable, and you're accessing the bit width, right? This is just like the assignment returns these. It's the bit width. It's a pair of the bit width and the x, which is the actual variable, right? So it's just a pair of the bit width and the expression. So if you're getting the ID, if you're getting the variable and you get the bit width of it, it's actually just equal to getting the bit width of the actual index here, right? So for example, like right here, right? It's just the same. And this is the second one, right? If you get the assignment and then you get x, it's actually just equal to x, given that you given that you rewrite the bit width, right? Because if you get this here, right, this returns self.n, right? So this is actually just, this is referring to this, right? But if you look at this, this does not refer to sigma at all. So you have to cast. So you have to do a cast. So you're basically, if you do this, this triangle operator basically means replace instances of this with instances of this. So then it's then this type check's okay, because if you didn't have this, this wouldn't type check, right? So this x has type this, which is what we wanted, because that's how it's defined. But it's expected to have type this, right? Because it refers to this sigma here. So we don't want to refer to sigma, so we just do this. And so these are just like well formed in this assumptions. And then the proof is just like this is this. This is super simple. So this isn't true. This isn't true like definitionally, right? This isn't true definitionally, but so like we have this theorem. This theorem isn't true definitionally, but these assumptions are true definitionally. These assumptions are true definitionally. So for example, if we have like this, right? Yeah, so like if we would like copy paste these things in here, the proof of HB would literally just be the proof of this would just be RFL. The proof of that would just be RFL. So I'll show you like how I actually get in the assumptions for eval var. Here, reify. No, actually do it in here. Okay, so basically this is prove var equals. So this is how it works. This is HB. This is the hypotheses bits. So you basically want to prove that this is true, right? So this is just equal RFL, and then you're casting. So these are definitional qualities. So the proof is RFL. It's just like super simple. This proof of H is also RFL. Then I construct eval var. This is just the index ID, the width assignment, this hypothesis bits and hypothesis. That's the proof. That's just the proof. So I return this out into this is the environment. So I construct the proofs ahead of time. So this map maps a like an x, right? It maps like x, for example. These free variables. It maps these to this. So this is the index. This is the IDX. This is the So if you have a IR var 0, this would be like this wouldn't be on here. Oh wait, no, yeah. So if you have an IR var this is a var ID. Okay, so this is a var ID. So this nat here would be 0 here. This nat ID will just be here. This 0. And then this thing, this expr, would be a proof that this. So this is like, I mean, the docs were right. So it's just a pair of these. So I return these out here, and prove var equals. So I just return this, this, and then when it comes time to reifying, right? It's basically just like I just get the map, I get the ID, I get the proof, I return this, and return the proof. That's it. So that's super simple. That's just how it works. So I think we can keep going. I think we can keep going. So what I have here is this add no sign wrap. This is how I've implemented like binary operations. It's basically like this. We get the left-hand side and the right-hand side. We reify both those sides. We construct the actual IR for those things. And then we construct the proof, right? So mk eval IR, what this does is it basically constructs this expression. So basically we have this, it's basically this, and the expression, LHS expression. We basically, so we have this. Because we reify both of these sides, LHS.proof is basically this equal to LHS.original exper. So because we reified, because we reified this is the type of LHS proof. This is the type of RHS proof. what we want to do is we want to chain these in such a way that adding these, right? So we want to basically take this now. So we basically want to say this plus no sign wrap this is actually equivalent to this plus this. So what is this saying? Basically, we want to take these two proofs, construct this proof, which basically says if you evaluate, we want to construct this proof is basically saying if you evaluate LHS expression. So this is just like this is what we have here, right? It's basically saying we want to construct a proof that this plus this eval of the left hand side plus eval of the right hand side is actually equal to the original expr plus the right hand side original expression. This is just it, right? And then from here, we can take this, and what we actually wanted was this, right? We wanted this. We wanted add wrap. Just expr. Is actually equal to this, right? So we actually proved this thing. This is the thing that we proved. But we actually want to prove this, right? We want to prove IR eval plus that is IR eval taking in the IR. So it's just like the IR add no sign wrap left hand side right hand side is actually equal to this side. So we basically like we prove the wrong thing. Like we prove this. We prove this. But this thing, this is definitionally equal to this. So it suffices as the same proof for if you eval the thing we just created, this thing, it's just equal to summing them. So this is like this is what I have this right here, right? So IR eval this is actually just like this, like no sign wrap left hand side plus right hand side. This is definitionally equal to just add no sign wrap as you like created the IR. So then we just return that proof. That's it. So like that's how it works. So you can sidestep actually creating the real thing, because it's just definitionally true. So the proof that I use for this to prove the first step, and then the next step is definitionally equal to that. It's just this thing. This is just super simple. It's basically if you have this, if you have taken these things, this hypothesis 1 is this is like forwarded to this. Hypothesis 2 is like this the thing on the right is forwarded to that. Summing these is just equal to this, and this is just true by equality. It's just like rewrite h1 h2, or you can just do the lazy way. And then what it is since I have these two equalities, right? LHS proof is basically eval is expr, and then RHS eval is RHS expr, right? So these two things go in as the hypothesis 1 and 2, and then this is how I like chain them. Chain the evals. So that's it. So this is how it works for binary stuff. So I'm gonna write down what we need to do, and I'll just do it. Yeah, then I'll just do it. So okay, do the thing. So really, when we do the thing, it's just like what did I do? Implement so yeah, binary operations. So like abstract the so I want to abstract this, right? Introstruct, that's not right. And then binops, and then what else? And then just like denoting. Okay, so that's what we're gonna do. Yeah. Okay. So just give me a bit. I'm gonna go to the bathroom. All right, give me a bit. Give me a bit. Give me a bit. All right, I'm back. Hello, everyone. Get back to work. Okay, let's just do it. So what needs to be changed first is this. This needs to be changed. So for example, here I have like add no sign wrap, etc. It would be nice to turn this into binop. I think. Wait, let me think for a sec. Would this make this more annoying? No, it wouldn't. It wouldn't. Okay. Yeah. Okay. My fault. So basically, how I want this to work is instead of this case, right? It should work like this. So we have iron add, and it's basically just like handle binop, bin up, reify bin up, reify bin, right? And then it takes in the the constructor ir dots. Just a constructor. So a constructor is just ir something. Oh, a constructor. It's just like ir idx, ir idx, ir idx. This is it takes in the constructor as well. And so, for example, I would just write like ir dot add. This is a constructor. This is a constructor. And then what next? Takes in the congruence lemma. What else? What else? What else? What else? What else? That's it. No, seriously, that's it. Okay, that's it. So that's super simple. All right. All right, and then I just make can I just use like it's like where go? Yeah. No, reify binops. I've never used this syntax. This is like a Haskell thing. I can just like look at the BV decide. Maybe I'm looking at the wrong place. This is the I really want this one. How do they use this syntax? Here, the syntax is like this. So it's basically you go to the top, it's just like go. Just like go. So I'm just gonna copy that. Reify binop takes in an index, a body, returns this, of course. Reify binop. You would put in I'll take in the LHS, RHS, LHS, RHS. It would take in the lemma. It would take in let's see. God, my hair is not cooperating today. God, I hate this fucking hair. Can't see shit. Yeah, so takes in the left hand side, right hand side. And then okay, left hand side, right hand side takes in the constructor. It takes in the constructor, which is this cons constructor. What else? What else does it need? That's it. Is that it? I think that's it. Okay, and then how does reify this? It's just like do. Like do. Alright, so I just move all this stuff. So is this thing? Is this just extra? Oh, that's annoying. I'm gonna copy all this stuff. Whatever. I'll just copy it. Okay, and then just expr. We want the IR. This IR is basically we want cons. We want the constructor. What is LHS? Where does that come from? Oh, whoops! I didn't copy this. Okay, we want the constructor, and then we want the quoted IR expression. We want cons as well. We want constructor, but we also want the name of it. Oh, that's annoying. Is it IR? It's the constructor. Two expert doesn't work. Wait, give me a second. Dots add. Okay, that's not a thing. What am I looking for? IR.add. What do I quote this, right? I quote this. Since it does synthesize implicit argument index, that's a problem. It's a problem. Okay, what's the type of this? This is this type. This is the type. Okay, I just select Han's name, just like the name. This isn't IR. This has type IR IDX IDX what about this? Right. Oh no. IR IDX. Wait, no, it's the type of this. It's the type of this. And this is a MK const. Yeah, MK const. Can't quote level M bar. Okay, what if I just like, just do this? Q this. Great. Okay, this should work. So, the reason why, like, I was just thinking, like, okay, why don't I just take this and then do this instead? Is basically, like, I can just write this instead. IDX, right? And then this is just like to expr to expression this. I could have just I could have just written this. The thing is that like this is like quadratic. This is quadratic. This is linear. The reason why is because as I recurse down, I'll be like recreating. I'll be recreating like this thing. Then I'll be recreating this, and I'll be recreating this, and I'll be recreating this. Right? This is quadratic. This is linear. Like it just like because I already have the expression. I've already constructed it. So I don't want to do 2expr on this. This is like pointless. Yeah, yeah, and then it's just this. And then this is just I just need the lemma. Lemma. I just need the lemma. Oh, lemma. Congruent. This congruence lemma is just like this. How's it supposed to work? What's the type of this? I just need to quote this. I just need to quote this type. This is a theorem. What's the proof of this? Sorry, one sec. Equates the expression t into that. All right, let's actually just take a look at what this proof is. So this is the proof of. Okay, so it takes in a nat, which is n. I think nat. And it returns a nat or something. Yeah, and so it takes in an n, and then LHS, RHS, LHS tac, RHS tac is INN. Okay, the thing is, like, why am I typing this? Fuck, there's no point in typing this. This is just a name. There's no point like typing it. Conger lemma. Conger lemma. I'll just move these to the top. I need to quote this. Fuck, so annoying. Fuck. I hate QQ. MK const. MK app. How many is this? 1, 2, 3, 4, 5, 6, 7, 6, 7. Yeah, MK app. NQ, just expert, right? Just expert. Just eval. Right, just eval. Just proof. Alright, just proof. Great. And then I just return this. Perfect. Did I even need this? I didn't. Okay. What else? I think that's it. Yeah, okay. So I just like replace this. So this entire thing is really just whoops. This entire thing is really just this. Reify binop takes in the index, LHS expression, RHS expression, takes in the constructor, takes in the name of the constructor, takes in the actual Conger like lemma, which is this. Hopefully that works. I think it's showed off here. What's the problem? Really? Oh, how it works is it takes in the IDX. Nat. This is like, yeah. Whoops. Whoopsie. Wait, but where does this happen? This isn't here. Oh, okay. This is MK const, but I need to app. I need to app this with NQ. Hopefully that works. Bruh. Okay. What? RAN leaf. That's not right. What's the problem? This is the constructor. Let me just check the check the expression, check the proof. Overloaded errors. Come on. Where's the problem? Add no sign wrap. Oh, did the wrong thing. This is supposed to be IDX. Whoops. IDX Q. Q nat. Yeah, my fault. I'm doing the wrong thing. It's supposed to be this index. That should work. Great, it worked. So return the proof. So this is the IR, so it takes in this, right? X plus poison plus X plus X. It returns this, right? This is the IR. And the proof, this is the type of the proof. The proof is basically saying if I sum this with the eval of this and then this, I get this. This is definitionally equal to having the IR eval on the outside. So when no JavaScript front-end framework. What do you mean? What do you mean front-end framework? You mean on my website? I don't use any of that stuff. It's just I converted it entirely into no client-side JavaScript front-end framework. What do you I don't know. I don't know what you're talking about. Yeah. What did I forget? Did I forget something? So when the client-side JavaScript front-end framework. I don't remember. Unfortunately. I'm sorry. I don't remember. Maybe I'm forgetting something. Sorry about that. Yeah. So okay. So this works. This works fine. And the proof is right. So here's the proof term. It's a big one. Which means yeah. But this is what we proved. So the IR eval, it's basically IR eval, no sunwrap IR eval. Well, this is just definitionally equal to IR.eval, like no sign wrap, summing them. So this is okay. This is just okay to do. So all right, we have reify binop, so then we can just duplicate this code a bajillion times. I can just like do this, right? So what's the? So I just add here, and then I need add no sign wrap conger. Need to do this proof. Add conger. Okay. And this should work fine. Okay. So yeah, we proved IR eval this plus this is just equal to this plus this, but that's definitionally equal to evaluating this entire thing. So that's it. That works. Okay, so I think the only two instructions that I use at the moment is just like plus and then no sign wrap. That's the only two things I use. I think I'll just like keep it like this, and I'll just go straight into denoting. I think that's fine. I think that's fine, right? Yeah. So I can remove this. And then usually what I do is I just put the current stream, this one, in the thing. What should I name this? What do I even do? Reify. Okay, implement. Fuck, I hate Copilot. Reification. Nice. All right. Denoting. It's the time for denoting. So denoting is the inverse operation to reify. Like I think I went over it. Yeah, I think I went over it in the beginning. So I guess I'll just go to that. Where is it denote? I'll just copy all the imports. Oh yeah, I didn't say, but since like last stream and this stream, I like changed the modules as well. So all the modules, like it's not everything's not in one file, which is better. So this is what I had, right? What does denote return? It returns the expression plus proof. Wait, let me think. Plus the proof that that thing is just equal to that thing when you denote it. Yeah. So this is proof and expr. Maybe I do it like this, right? Maybe I do it like this. Maybe I make a structure for it. Original IR, IR this, and then proof. Original IR equals what? Original IR and the expression? Oh, I just like expr. I don't want to write expr. It's just expression. Okay, so it just returns this. Great. So this should be okay. This should be easier, I think. This should be easier. So if I var ID, it's just the inverse of that. So given a var, oh, I need to go the other way around. So I need to map IDs to proofs. So what I have here, I have this thing, sigma map, right? This maps expressions to their ID and proof. But I need to go the other way around. I need to go the other way around. Which is basically like I need to map var ID to proof. I need to go the other way around. Maybe I just do like map sigma, like I have here. Okay. No, this is an array. This is an array of FRID and proof. That's annoying that I have to like keep this like stupid map. And this thing, map xi, this should be an array as well. Yeah, this should be an array. I don't know, why is this not an array? Oh, I mean, okay, this is just like this. I guess this takes in this. This is just an array. Ah, crap. What did I do? This is an array. It's just this. This is the width assignment. Actually, these are just arrays. This is just width assignment. Okay, so this is just like yeah, these are just width assignments. Like I already have these. This is kind of like the inverse. All right, what's this one? This goes underneath. All right, what am I missing? Insufficient number of fields. So I need this. Var ID to expr. I need to go the other way around. This is annoying. I need to go the other way around. I've already nat. What's this an array? This is an array of assignments. Okay, and then this is map sigma. Map sigma. Map just takes in function it dot what is this returning? This is an array. So this is an array from it's FRID and expr, so just like this tuple. It dot what? Like what is this? This is just this. FRID fr nat expression. This proof. Just fr and proof. All right, what's wrong with this? Expected type. Yeah, fair enough. Maybe if I just put this here. All right, that's not that bad. This is this thing. App sigma. I want this thing. I want to go the other way. So I want to change this ID. I put the bang there, so I want it to crash. Yes, FR. And what's the other one? Proof. Okay. What do I return? What do I return? Is it just like I think it's just the same. I think it's like literally the exact same. Return mk fvar. Well, of course, because we need to return an expression. This is the expression. This takes in the fvar expression, the original IR, which I guess that, and then the proof, which is just this. I think that's it. I think that's it. We'll give this a try. Right? We'll give this a try. In OPT. What's the problem? Why is this having problems? Reify. It's here. Okay, so this is reify. And then okay, but what we want to do is we want to run this in this. Yeah, okay. Just doing this wrong. Okay, so we add the IR, and then we want to go back, body tack, just like we want to import denoting as well. Come on. Yeah, we want to denote. IR? What else? This is reified. Okay, so we, IR dot I don't know why this is IR expert. It should just be called IR. Oh, maybe just like AST or something. Fuck it, yeah. And then is it the new body? Okay, and then we get this thing. So this is body, and then body dot proof. Yeah. Okay, so we want to do this, right? We want to check the proof first, foremost. We want to check the proof. Reify proof. And then we want the body proof. What would I call this? New? RHF? RHS? Okay. What's the problem? Oh, well, obviously, there's like a sorry there, so just like throw. It sounds like a throw error. Just on. Is it like a throw and implemented? Unhandled, throw something, unhandled, throw. I'll just throw error. Unreachable. So it's unreachable now. A failed to unfold definition. What are you talking about? Okay, well, this is just unreachable. All right, and this is the only thing we handle. Okay. So reify proof is this, denote proof is this. That's just the exact same. So we'll just do more. We'll just do more. So yeah, so we have denote and reify. Yeah. Should we try and chain these proofs together? We'll wait. We'll wait. But yeah, okay. So we have reify, it's the proof. It's a proof term. And denote, just this. So yeah, let's just get to doing it. Let's just do a bit. We'll just do more. So it's really just the inverse. It's just the inverse of reify. So just poison. Like these things are like seriously, these things are just it's just more of the same. Maybe I should make this like a proof. Not a proof. Like a function. Because this is just like a function as well. The proofs are the same. That's annoying that I have to duplicate. I have to duplicate this work. Wait a minute. Wait a minute. No, no. Okay, I was thinking that like, oh wait, what if this is reified? I can just like invert the whole thing. I already have the proof, but no. This is just like an arbitrary IR. I can't use the previous proofs I constructed, like not at all. Yeah. So I guess I have to duplicate this work, which I mean, fair enough. That's fine. What do they import? They import from here, right? Reflect. Proof. Because this is just like RFL. Yeah, okay. So I'm just gonna have to duplicate the work. All right. I'll handle binops now. This takes an IR. These are two expressions. No, they're not. These are two IRs. What the hell am I talking about? And then we would want to take in the fun's name, inst name. Um, That's annoying. Duplicate work. Whatever. Read. I swear I can just copy this entire thing. I swear to God. And then just like change two things. I'll copy it and I'll see what I can like make into a function. So what I'm returning is, so I don't need this, right? Technically, I need this. This is body. And that body is an expression on mk app inst name. This takes in an enq. I want to mk app this with what else does this take in? Nothing. RHS IR. What else? What else? What else? What else? LHS dot okay, app2. Okay, yeah. So this is the sorry, this is the expr, right? That's expr. So it's basically creating LHS just like denoted. These are the like denoted versions. Okay. This is an expression of type INN, and then basically you want to chain these proofs. You want to chain these proofs in the same way. Surely this is like basically the same. This is like expr. Original IR. So this is who gives a shit? No one needs this. The original IR. Yeah. Wait, so what do I do here? Where's body come from? What? Oh. Huh. These aren't separate these functions like can take from the top. Interesting. So I don't need this argument. This IDX refers to that. Okay, that's nice. That's nice that exists. Okay, so how's this gonna work? So this is so in here we want original IR. So this is the expression. What's the expression? So it's just body, IR, and pure proof. Didn't need that. Let's just hope this works. inst name, and then under. What's wrong? Oh, there you go. Surely that's fine. All right, let's see if this works. Does this have an incorrect type? No, it's got the right type. Why is this no sign wrap? Why is this no sign wrap? Is this taking an add? Shouldn't this throw an error? Shouldn't this throw like an exception? No, I mean this is right. Maybe I'm matching on the wrong thing. No, I'm not. What the? What? Am I going insane? I do add here, right? I get an add here, but where's this coming from? Why am I getting add no sign wrap, but I have like an add here? Maybe, okay, hold on, okay, my reify is messed up. Okay, yeah, so I've add no sign wrap here as well. Whoops. Whoops. That should be fine. Unreachable. Oh, because I just don't handle it. Okay, I'll just handle it. Add. I'll just like duplicate this. Okay. I'll handle poison, and then this is just like fine. Then I can just do then I can just jump right into optimization. So I think because like I'm just gonna implement like basic stuff, like the things that I need, and then I can jump right into optimization. The proof chaining, the original idea of all of this. So poison. I'm just gonna copy this. So annoying. What the fuck? Just copy it. Poison. So all of this can go. What this basically is, I'm returning the quoted expression in.poison. I mean, like, what are they leaving out? This is just like, this is this. Expert is in. Poison. This is what I'm returning. So, okay. Let's make this. I'm just like change this stuff. To expert. Like we already have this. This is like not. should I change this? Because like, what I do here is right. This is fine. Okay, and then I just quote ir.poison. This thing's also here. Sigma q. In the synthesize implicit argument index, this is ir. Maybe that's a problem. Okay, that's fine. LHS, this is actually equal to the body. Okay, what's the body? Have body, what the expression we are, what we're returning is this as well. Q poison. Wow, that's it. And then it's literally just like, what are we returning? This is the expression. This is the expression. This is the expression. Body Q. The original IR is literally body. And the proof is just this. Okay, what's the problem? Oh. Alright, that wasn't that bad. That was actually easier. Maybe a lot less code's being copied. Alright, let's just take a look. Oh, come on. What? Unknown identifier poison. Unknown constants? Dude. Maybe here. Maybe that's the problem. Please. Oh, what? What's the problem? Unknown identifier poison. Surely it knows what I mean, right? No, it does not know what I mean. What? Surely it knows what I mean. That's fine. Okay, what if I take this out? Okay, this type check. So why does this not type check? What? Why is this type check? What? The error just went away. Okay, sure. I got eval. Poison. No, okay. This is wrong. The types are wrong. Like if you check the types, right? If you check the proof, if you check the types are wrong. And the types is just straight up wrong. Because like this does not go into eval. This is not IR. This is not IR. Okay, so that's how does that happen? This happens in denoting, right? Yes, it happens in denoting. That's a problem. MK eval IR. Oh, that's wrong. Okay. I guess returning the original IR is pointless because you pass it into the function. It's like, what the hell is the point of that? It's just no point. Um, failed determination? What the hell are you talking about? Oh. Uh, okay. Oh, that doesn't even take in a meta M. Okay. So, okay, to do, eventually make this, oh, wait. I don't want this to be quadratic. This is IR, unfortunately. This is IR expert. That's not how you spell that. Yeah. This is IR expert for a reason. I don't know this to be quadratic. Okay. Why am I calling eval IR? Am I like stupid? What? Wait. This is like all wrong. This is all wrong. Because why am I calling MKE? Why am I calling eval IR on this? This is supposed to be LHS dot IR Expo. Okay, this is all messed up. Maybe. I think. That's MK app 3. No, this is just this. IR. No, I need to do it this way. Congo lemma, and then this is instruction name. On On's name as well. Yeah, just give me a moment. IDXQ. Where does that exist? Does it exist up here? Great. Cons Q. Maybe this is right. But what about this? Okay, let's see. Oh, did it work? So it checks? I think it checks. I think that's right. I think it checks. Yep. And then what's this one? This one's a big one. Yeah. Yeah, that's it. That's it. That's it. That's it. We did it. Okay. All right, very good. Things aren't going that bad. Implementing denoting. What do I want to change before I commit this real quick? LHS. No, this is just IR. IR.IR. I hate that I have to write that. Okay, whatever. IR.IR. Okay, reified. Reified. Much better. Okay. Git log. Good. Very good. All right, not bad. We can tick these off. Okay, so we're actually, stuff's getting done. What next? I think we can do proof chaining, and I think we do optimization. Why can't I go down? Why can't I move? What? Oh, because that's the end of the file. Stupid. Okay. We'll get to work. So, proof chaining. So, we have reify and we have denote. So we have these two proofs, right? We have these two proofs. What we basically want is to chain them. We have this. This is by definition. So for example, the reason why it's by definition is because we have this WF here, right? So you can basically, if you have IR, right, you can make IR tac. You can make a new one where it's just this dot import IR, right? But you can also prove that this is the right one. So like add refine add tac well formed IR, right? This is also a proof of correctness. That's proof of correctness. So yeah, I think we can just get doing it. We can just start doing it. So we basically want rewrite. This does the proof chaining, which like that's super cool when it does that. So def. This is a function. This is reify, right? This is just like opt-in chain. Opt-in chain. This takes in a R rule. And this takes in oh wait. How's this gonna work? Let me think for a sec. This isn't like sort of right. This is how it's supposed to work. You have IR tac, and then you have let's just say let's just like hard code the optimization that we care about. Let's hard code it. So we'll go like rule is a rule, and just add New South Wales defined New South Wales, no sun wrap define add. This is our rule. So we have the implementation, and then the well formed assignment. Should I remove some of these things? Maybe I remove to make this easier for the time being, I'm going to change the definition of this. Yeah. We have okay. Yes, I just changed this. So the well-formedness is taking the width assignments, the assignments, and then we can just rewrite them. So, yup. So you just take this, start file. Okay. What's the proof of this? Wait, did I write this wrong? Oh, this takes in an index. Whoops. Yeah, so it's supposed to be like this. Yeah, that's the IDX. It doesn't matter. Okay, the proof is perfectly fine. That's it, that's the proof. Okay, and then we'll do this. So we want to optimize. So rule, implementation of that rule, IR, reify. We optimized. That's it. Optimization has been complete. Okay. What now? We want the proof as well. Up to well formed. Taking the rule, the index. Oh wait. Okay. Yeah. So we'll just construct. We'll construct the proof as well. So we'll construct the proof like this. MK add. Construct the proof like this. Yeah, MK add. Add no sun wrap, refine, add well formed. Yeah, we'll do like this. Let me think for a second. This will apply it on the root. This will apply it. So we'll apply it on the root, which is what we want, really. I'm gonna change all this crap. Give me a moment. So I'm gonna change this to basically allow you to put in a rule. So I'm just gonna allow you to like do that. It's like, okay, I'm putting in this rule, and then you apply the rule. So I think it's just like, I think let's just do it like this, right? Like that or something. How about that? That's fine. So then we just have I'll just like get rid of this for now. Comment that out. There's rule syntax. We want to elaborate this. Type rule. I don't identify a queue. I don't import QQ. Maybe I should. Okay. So here's this rule. So what we want is we want the implementation, and we want blog not working. What happened? Did something happen? What are you talking about? No, it works fine. Do you mean this? This one's dead forever. The /me. It's too cringe. But this is fine. This works. Looks stream. Comment a bit, yeah. Good to see. Yeah, this works. Yeah, this is dead. This is dead. This thing's dead. This thing's just dead. It's not coming back, unfortunately. This isn't. It's just dead forever. Maybe like maybe I put a notice here, or find a way to archive it. But at the end of the day, like most of the images on here is gone. Like most of the images on this blog are gone as well, because I use like Discord CDN for this. Eventually, like I just neglected the shit out of this like blog. It's like not. Fortunately, it's just not coming back. Yeah, yeah. Uh, how I would attach images on that site is I'd like paste them into Discord and then like copy the CDN link and then paste the link in there, which was stupid, and that's how I ended up losing the images. Well, the images aren't lost. They're like they exist. It's just that I'm gonna have to find them again, and it's like the stuff there's just not worth saving, fortunately. I have all the archives though, so I might like put a notice up or something. I might put a notice up, but yeah. The me like blog, it's like come back in this form. This is just my stream schedule, but yeah, unfortunately. Fortunately, that's just down forever. So I have this rule here. I want to access this function and run it. That's a problem. I want to access this function and run it, and then I want access to this proof. Accessing this proof's fine. Right, because this rule, this is just a type cute rule, right? It's just this, right? To access the well-formedness proof, it's just this, right? Q rule dot well-formed. What's wrong with that? What? Synthesize implicit argument index. There you go. That's how I access the well-formedness thing, right? Because this exists as like a meta, as a theorem, right? This is more like the meta code. But running this is going to be like annoying. How do I run this? Is there a way to access the like interpreter? Well, I mean, this is how you access the interpreter. You use unsafe code. So eval please impl. Does reify IR expert return a it returns the IR. Great. It returns this. Great. Okay, so I'll just do it like this. Run impl. Eval impl. This takes in a it would be just like a quoted rule. This takes in an index, the IR expert, which is really IR IDX. This takes in this is the rule, quoted rule. This returns a IR. Great, and then this is just copying. This is just copied. So how this works, I'm guessing, is I'm just gonna need this. Yeah, you have to use unsafe code to actually evaluate this stuff. So let's just create the expert, which is just really this. Rule.wellformed. And then I'm passing in, oh wait, not this, not well-formed, impl. Impl. This takes in the IR expert. And then I want to do this, right? IR IDX. What's this type? Expected type. IR IDX. IR IDX. And then expert. That should work, right? All right. Yeah, this is unsafe code. Definition safety. Yeah, okay. Yeah, this is like you have to use unsafe code for this, which is annoying. Eval impl unsafe. But I mean that's okay. All right, and then so to access the optimized code, it literally just like suffices for me to just like take this like this. So I just go like let's optimize. So the IR tac is this result index. The reified IR expression, the rule. Yeah. What's this? What's wrong with this? Oh, this is unsafe. Well, I want this one. Yeah. Okay, this runs it. This runs it in the interpreter, right? Oh, yeah, this runs in the interpreter. So then this gives me just the IR, and then this one. I denote this one. Okay. What did it do? Yeah, okay, so what does this optimization do? It replaces, if it can find add no sign wrap in the root, it'll replace it with this, right? If you look at the implementation, it's just like IR. You match here, it just replaces it with add, and then else returns that. So we'll just like make this do this, right? Add no sign wrap this, right? What's wrong with this? Okay, and then yeah, so this is the reify proof, such that like yeah, we turn this into the IR. That's okay. The denote proof is after so yeah, so this is the it's like IR var 0 plus no sign wrap IR var 0. And this is IR var 0 plus uh IR var 0. So this is okay. So it actually optimized. So yeah, so running the implementation, yeah, it optimized. So now we just need to chain the proofs. So chaining the proofs is gonna get I don't know if it's gonna get annoying, but we just need to chain the proofs. So here it is. Here are the proofs. So first we reify, we opt, and then we denote. Yeah. So okay, so chaining the proofs would just be I guess we'll do this, right? Law form proof is q. For my quick note saving, I just save the screenshots images inside the HTML base 64. Huh. Huh. Interesting. Content editable. Nice. That's interesting. Yeah. What I do like right I embed the images properly now. This is like media. This is like under media. All the images are properly embedded. So previously I had like for me .l-shem.dev, I had a it was a web editor. It was a web editor. But now this is just like markdown. So these are wiki links. These are wiki links. And then I have a bunch of like Lua scripts to transform them. If you take a look at I think it's this one, right? This one. This is like my site now. So everything's here. I have where's the tools? Just like resources. So I have like Lua scripts to like convert all of this stuff. Like this uses Pandoc. This uses Pandoc. So it all works like normal. Yeah. Much better than like using a web API, like not a web API, like a web interface to edit. I just use like Markdown. So law form proof is just dot law formed. Sound pasting of images. Huh. Oh, that's pretty cool. Yeah. So it's just like it's just all in what's it called? Yeah. Paste bin. That's nice. It's actually pretty nice. Everything's all in HTML. Yeah, it's actually pretty good. I've never like thought to do it that way. Just take something with this one. So okay. I'm gonna make a function to chain these proofs. Yeah, so here. Chain proofs. So this takes in the reified. So the reified IR. So this is the result. So this takes an index, right? Nat. This takes in the reified IR. Reified. This is LHS actually. reified IR. And then what else is it taking? So this takes in the reified IR. This takes in the optimized IR tac. This is IR IDX, optimized IR. And then we want to, yeah, so we denote this IR. So this is denoted IR. IDX. And then basically this takes in the theorem. Yeah, the well-formed theorem. This is well-formed expression. Okay, hold on. What does well-formedness actually encode? One sec. Yeah, I'm not typing that out as a quoted thing. This is just like an expression. Right? It's just an expression. This is basically Q for IDX sigma sigma this. And for YouTube video links, I have it hooked up to YouTube DLP. Huh. Yeah, okay. Yeah. What I do is like in my Obsidian Vault, it's just like a list. It's just like a media folder. So I guess I'll have to manually put in the videos and stuff. Yeah. But it's just a media folder. And this takes in the, this is basically for all this LHS rewrites to RHS. No, this is basically saying LHS rewrites to, is basically saying IR rewrites to tac, basically. And then this is what is this returning? This is meta m expr. This is the proof. It's not meta m. So yeah, okay. So we'll just use chain proofs. Construct proof. Construct proof. Why is it taking so long? Reified. So this is IR. Oh no, this is reified. Reified. IR tac. And RHS. And we want the well-formedness expression. So this is just rule. Why is this big? Is that necessary? Why is this big? Anyway. It's gonna make it less big. Lean is so slow. Maybe I'm not using the module system. Okay, that's fine. Yeah, Lean has an experimental module system, which makes this better. Yeah. This is rule dot well formed. Yeah. Okay, that's fine. Okay, and then proof, and we just want to print the proof. So I just want to check the proof, and we want to print the proof. We want to print what was actually proved. Proof. Great. This does nothing at the moment because it's not implemented. Whoops. Yeah, this does nothing at the moment. Yeah, not implemented. So we need to implement it. All right. So this is just proof training, chaining. So how's this supposed to work again? So mk app something mn. What does mk app m do? Oh, okay. mk app. It's not universe polymorphic. No, it's not. Okay. Mk app from expo, and we want with assignment assignment. Then we want the LHS IR. Why is LHS not like? Oh, really? LHS dot what? IR expression. Yeah, IR expression. And then this whole thing is a proof that this rewrites to the optimized version. Right? Let me think. Um this calls into implement here. This seems like a problem because I have the concrete IR here, but I don't have a proof that this IR was actually created by running the implementation of the optimization. I actually don't have a proof of that. How do I get a proof that this is the thing? Seems like a problem. I don't know. Maybe what I can do, right? I can do lean of reducible, something for example, right? I can do, well, okay, what I can do is, so I have IR and I have the IR tack, right? This IR tack is really created by running impl on the IR, right? But we don't really have a proof of this. So I guess what we need to do is make a theorem, right? T, IR equals IR thing, right? IR equals impl IR. No, sorry. This is this, by decide. This is like a decidable proposition. You can just run it. Like, you can prove this by deciding it. I'm gonna have to look in. I'm gonna have to look further how we do something like this. But since this is a bit of a roadblock, I might cut it off here. Yeah. But it was good. Good stream. Like we did a decent amount. If we take a look, right? We did these two, denoting and that, and we got up to here. So I guess I need to figure out the stuff around this. Right? I need to figure out the stuff around this. But that's okay. That's okay. So I think that's it. I think I'll call it off. So it was good. Thanks everyone for coming. I appreciate it. Appreciate it a lot. Goodbye everyone.